Hello, I'm Colin Scot, and I'd like to talk to you today about potential benefits of vanadium microalloying in advanced high-strength steels and cold strips. And now this talk I have 4 co-authors that I'd like to mention. There's Irina Pushkareva and Fatih Fazli from CanmetMATERIALS. That's the lab where I'm working at the moment. And we have David Milburn, Yu Lee, and Bob Glodowski from Vanatech. I also would like to thank ArcelorMittal because some of the data I'll be using in this talk was obtained at the time when I worked for that company, and they've been very generous in allowing me to present it. The talk's broken down into 4 or 5, I suppose, main parts. There's an introduction, and then I'd like to talk directly about applications, and the 3 applications I have in mind today are ultra-high strength trip steels, 1000 megapascals and upwards. The little arrow means above that strength level. DP steels, Dualphase steels of 1180 megapascals or more, and then an industrial application to high strength manganese twip steels. That's a project that I was very deeply involved in for a long time, so I do have quite a lot of experience about vanadium in that particular material. And then we'll wrap up with some conclusions. Now, vanadium has a strong presence in what I would call hot product microstructures. These would be ferrite, perlite, bainitic, tempered martensite type of products. But in cold rolled and annealed sheets, in advanced high strength sheets, there's very little use in industrial products. Now, there are many reasons for that, but one of the main and the main historical reason is the cost. Vanadium was subject to quite unpredictable price fluctuations a while back. And that meant that people who were doing alloy design, people who were involved in product specifications, didn't want to use it because they couldn't predict how that would affect the end profitability of the product that they were making. Luckily, fortunately, these price fluctuations have kind of leveled off a bit now, and that argument has decreased in strength. So people are turning back and looking again at vanadium in a more serious way. There is also a window of opportunity for new steels, these advanced high-strength steels that this talk is centered around. These can be first generation, second generation, and third generation steels. I'll explain to you a bit later on what that means. These steels are actually being developed now, and there is an opportunity, a window of opportunity, I would say, to change this situation so that vanadium could actually become a useful material and a useful addition to these new steels. Now here we are. This is a very standard chart that people who talk about high strength steels or any steels for automotive industry use. We call it the banana chart. You can see the banana there. It's an elongation against ultimate tensile strength chart. So you can see that you would have in this upper corner here very ductile steels but very low strength steels, moving down to this corner here where we have very, very high strength steels. These would be martensitic steels, press hardened steels for example, but they have very low ductility. And all of these steels here are contained in this banana shape. A while back, in around about the year 2000, we decided there was a way found to break out of that banana, and this would be using these twip steels, which are austenitic high manganese steels. They have very interesting mechanical properties, you can see, breakthrough properties, so they are very much stronger and also very much more ductile than the steels inside the banana. Now the steels inside the banana, we would call them generation 1 steels. The steels inside this red ellipse, that would be generation 2 steels, and we're now developing something called generation 3 steels, which are intermediate. These ones were high manganese steels, and the green ones are going to be probably medium manganese steels, so slightly less alloying content, slightly lower mechanical properties, but possibly better in terms of cost, production cost, etc. So vanadium could be employed in these 2 areas, generation 2 and generation 3. Now just to show you, this is an example that Dr. Wang from Baosteel kindly gave me. It's the volume of ultra high strength steels produced by Baosteel as a function of time, and you can see from 2009 onwards the extremely fast growth in the use of these steels in Baosteel, and that's just a reflection of the Chinese market. So it is a very strong growth area, and if we can get some vanadium inside some of these steels, then that would be very interesting for the future. Okay, now first of the applications is to transformation-induced plasticity steel, trip steels. I would like to say that most of this work was done by someone who was working with me at the time called Fabien Perard. He was a postdoc, and it was done at ArcelorMittal. The postdoc was actually sponsored by Vanatec. Now you can see the microstructure on this image here on the right-hand side of the screen. It's a very complicated steel microstructure. There are three phases present. There's ferrite, there is bainite, and there is residual austenite. The residual austenite phase is in white in that diagram. Trip steels, transformation-induced plasticity steels, are very complicated in terms of their microstructure and their mechanical behavior, but they do have some excellent properties. Now, the problem with trip steels was they actually didn't get sold very much, and they still aren't very much sold. And the reason is they're difficult to make. They have microstructural inhomogeneities, so they have variations in in-use properties. They have some problems with weldability because they generally need quite high carbon contents. And there is a problem with coatability because most of them have fairly high silicon alloying additions. Although there is a variant with aluminium alloying which avoids that problem. However, it introduces other difficulties, especially with casting. Now, I mention all of this because third generation steels are essentially super trip steels in a way, and they were going to suffer from the same problem, so we have to find a way around them. We have to find a way to avoid the same fate. We were looking at these steels in 2006, and we wanted to know if we could improve them by adding vanadium. So here is the thermomechanical processing. I guess it's a diagram showing you all the intermediate steps from the hot band on the left-hand side to the cold band on the right-hand side, with cold rolling in between. You can see it's a very complex thermomechanical procedure, and that is actually, well, it's something that can give rise to problems in production because at any one step, the control of temperature, the control of time is critical for the final microstructure. So here we have some of the alloys that we actually cast, A, B, and C in this case. We had a reference heat A with no vanadium in it, and we had heats B and C where we added 0.1 and 0.2 vanadium. There was also another heat which I'll be using further on which had 0.15 vanadium, but it's basically the same base composition. There is nitrogen in these alloys as well because we wanted to see what effect nitrogen additions would have on the precipitation of vanadium carbides, carbonitrides. The titanium is given. It's residual titanium, we didn't add it, but it is important because vanadium precipitation is strongly influenced even by residual levels of titanium in your steel. So on the left-hand side, the microstructure is the reference steel. We have 0 vanadium in that steel, and on the right-hand side you can see the microstructure once we've added 0.15% vanadium. This is the final trip microstructure. It's very much refined. I'll show you later on that the mechanical properties are very much enhanced by this vanadium addition. The question was, is it due to precipitation or is it due to this microstructure refinement? And I'll tell you right now, we ran a structure properties model that we had developed at Arcelor, and it showed that although the properties were improved and there was a component of that came from the microstructural refinement, it wasn't enough to explain the increase in strength. So we do have a precipitation effect. So that's shown on this slide here. What you can see on the left-hand side, we're plotting yield strength and ultimate tensile strength as a function of the intercritical annealing temperature. That might seem a bit of an odd thing to do, but as I mentioned before, these steels are very heterogeneous sometimes, and they are very sensitive, or they can be very sensitive to parameters like the intercritical annealing temperature. So that's why this graph is plotted in that way. Now the blue points are the reference points with no vanadium, and the red curves are the curves that we obtained once we'd added 0.15 weight% vanadium. You can see that at certain intermediate temperatures, intercritical temperatures, excuse me, we have a gain of almost 200 megapascals in the ultimate tensile strength. And that is an extremely useful an extremely useful property that vanadium could give these steels. On the right-hand diagram, we're looking at the change in the ductility that's associated with that. So the blue curves again are the reference steel, and the red curves are the steel once we've added the vanadium. You can see that we do lose a little ductility, but it's actually very, very small, and it's not a real problem for the type of applications that these steels would be used for. These are very, very high-strength steels, 1,000 megapascals. If we can get something like 25% of total elongation, or over 20% of uniform elongation, that's a very, very good product. The thing I would like to talk to you about later on in this presentation is the sensitivity of these properties to intercritical annealing temperature. You can see, if you look at the left-hand diagram, the yield strength and the tensile strength are not very sensitive to intercritical annealing temperature, over the range 775 to 815 Celsius. But when we add the vanadium, we do see an increased susceptibility, an increased variation in these properties with temperature. And one of the objectives of the study that we did was to actually find out why that occurred. Because obviously if you don't control your intercritical temperature, then you're going to have these potential properties variations. First thing to do in any study like this is to say, well, what is the vanadium actually doing? When does it come out? When is it in solid solution, and when is it precipitated? So here we have, on this diagram here, these are data taken from selective chemical dissolution experiments. What we would do is dissolve the matrix, and we can measure the amount of precipitated vanadium in any alloy at any point along the production cycle. So there are two alloys on this diagram. I would really like you only to concentrate on one. This would be the blue one here, where there was 0.1 weight percent of added vanadium. So this is the total amount of vanadium that was added. Here we have the nitrogen content as well. Now, in the as-cast ingot, what we found was that of that 0.1 weight percent, we had just over half that was precipitated in the ingot itself. Then that ingot was reheated and hot rolled, and we quenched it after hot rolling from 900 degrees C. Now, vanadium is very soluble in austenite, and what you can see in the diagram is that what we have is that all of the vanadium's gone into solid solution. There's very little precipitated at that point. Very interesting property that vanadium has, because it means that we're not doing anything really to the hot strip microstructure. We're not strengthening the hot strip microstructure, so we're not going to be loading our hot strip millings, for example, and that can be one of the problems with these high strength steels. So vanadium is very good for that. Then obviously you don't do this in industrial practice, because you end up with martensite and you can't do anything more with it. What you'll do is you'll do a controlled cooling and then a coiling. We chose to coil at 540 degrees C here, which is quite accessible for most lines. And again, you can see that we did get some increase in the vanadium precipitation, but not very much. So we've managed to keep most of the vanadium from here in solid solution up to here. Then we did cold rolling, and we did continuous annealing after the cold rolling. And we looked at the vanadium and the vanadium precipitation after that step. And what we can see is that we actually increased significantly the amount of precipitated vanadium, in the steel, up to a point where we actually had more than we had precipitated in the original ingot. So this I'll explain in a minute. Question is this extra precipitation here measured by this dissolution technique, is it due to new precipitates formed after cold rolling, or is it due to growth during the annealing step? Here we have TEM data showing the size distribution of the vanadium carbonitride precipitates at 2 points. The red bars here, this histogram here was taken from the hot strip, and the blue bars here were from the cold strip. What you can see is that the mean radius of the hot strip precipitates is about 7.5 nanometers as measured in the TEM. Whereas in the cold strip, the blue histogram, we have a decrease in that mean radius, and it actually drops down to about 5.8 nanometers. Now, we've already measured the volume fraction precipitated in the cold strip. We've shown that it's higher than in the hot strip, and we have a smaller mean radius. So there's only one possible conclusion for that. These extra precipitates that come in the cold strip are new ones. They're not, it's not growth or coarsening of the existing precipitates from the hot strip. Now, we did some more TEM work on that, and here's a few images to show you. This is an experiment where we took the cold strip and then heated it up and quenched it as soon as it got to the intermediate annealing temperature. So that would be 775 Celsius in this case. What you can see on the left-hand side is a rather coarse extraction replica image, and at that point what we have is a ferrite microstructure, semi-recrystallized ferrite microstructure with quite coarse cementite precipitates which haven't yet dissolved once we get to the intercritical annealing temperature at a time of 0 seconds where we quenched this sample. On the right-hand image, if you look around about those cementite precipitates, we can actually see some very small vanadium carbonitride precipitates, and there are some rather coarse titanium vanadium carbonitride precipitates. The titanium precipitates would come out in the hot band, and the finer vanadium carbonitride precipitates actually mostly precipitated during this heating cycle after cold rolling. On this slide here, we've actually tried to quantify the precipitation state as a function of the soaking time at the intercritical annealing temperature. And we did this at two different temperatures. We did it at 775 Celsius and we did it at 815 degrees Celsius. Now, if you remember, the mechanical properties at these two temperatures were quite different. We had quite a lot of softening in the ultimate tensile strength at the higher intercritical annealing temperature. These graphs can help to explain that. So what you have on them is, this is from TEM data and a combination of TEM data and from these selective chemical dissolution experiments where we could get the total amount of vanadium precipitated. And you can see, for example, here we have a number density. So at 0 seconds, we have a very high number density of vanadium carbonitride precipitates. And as we go into the intercritical annealing soaking, that number density actually tends to decrease. The mean radius is very small at the beginning, and it's actually growing. And the total amount of vanadium precipitated is fairly constant. There's a small increase in there. So this would be consistent with some kind of dissolution, because the number of precipitates is going down, and growth here. On this graph, it's slightly different at the higher temperature. First thing is that the number density is already much less. So that suggests that in going from 775 up to 815 degrees Celsius, we've lost some of the precipitates, that we formed in the lower temperature case. I should mention that the heating rate here was 5 degrees C per second. So also on this right-hand graph, you can see that the amount of vanadium precipitated is a bit smaller, and the mean radius is actually higher. So these data show why this particular annealing condition results in a lower ultimate tensile strength than the one on the right-hand side. We have less precipitates globally, and we have a higher radius of those precipitates, so they're less effective at strengthening. Now this is a global picture. Inside the intercritical region, we are in a two-phase region. We have ferrite and we have austenite. And this picture doesn't tell us what's happening in both of those phases. So we actually did some interrupted quenching, and we tried to find out in the TEM how these precipitates were distributed between the ferrite and austenite phases. And it's actually very interesting. This image here is the final microstructure. So we've gone through 180 seconds of intercritical annealing, and then we cooled it at 20 degrees C per second and overaged at 300 seconds at 400 degrees C, for 300 seconds at 400 degrees C. If you look at this microstructure here on the left-hand side, it's very interesting. You can see it's an extraction replica. Obviously, I should have said that. You can see residual austenite islands. You can see areas which we think are intercritical ferrite, and you can see other areas that we would assign to benitic ferrite. The distribution of precipitates is very heterogeneous. We don't see any at all in the residual austenite, very high density in the intercritical ferrite, and very few in benitic ferrite. So the image on the right-hand side is just it's an increased magnification image of the same microstructure, and you can see that more clearly. There's a large density of vanadium carbonitride in the ferrite, virtually none in the residual austenite, and very few in the benitic ferrite. So it gives you a selective strengthening of the ferrite phase, and that is something that is extremely interesting, because in these microstructures that's exactly what you want to do. You don't want carbides precipitating in residual austenite, because that is just going to use up valuable carbon that should be in solid solution, stabilizing that austenite to give you a good trip effect. You don't really want to precipitate in the benite either, because it's not going to give you a very big increase in strength. The phase to strengthen is actually the ferrite phase. That's the softest phase, so it's the most interesting one. So this is exactly what we want to do. Now, we went a little bit further and we said, well, that's very interesting. Why is that happening? These extraction replicas were not carbon replicas, they were aluminium oxide replicas, special replicas that we made to do this particular type of work, because we wanted to see how the carbon and the nitrogen were distributed inside these carbonitride precipitates. So what I'm plotting on this graph here is the atomic ratio of carbon to nitrogen along the vertical axis, along the y-axis, as a function of the precipitate diameter. So as we go higher up this axis here, the particles, the precipitates, are becoming richer in carbon. Lower down here they have more nitrogen in them. And there are two different colors of points in here. There are the very light blue points, which are precipitates that we measured in the austenite phase, and the dark blue points are precipitates that we measured in the ferrite phase. And what you can see, first of all, in the austenite phase is there's no relationship between the size of the precipitate and its carbon to nitrogen ratio, its composition. It seems to be quite random. Whereas in the ferrite, in the ferrite phase, it's completely different. The smallest precipitates are always very rich in nitrogen, and the biggest precipitates are rich in carbon. That is a very strong indication that what we have here is actually growth coarsening in the ferrite phase, and in the austenite phase we don't have anything at all like that, so no growth or coarsening in that phase. And this could be explained by the following schematic. So what I'm showing here is the intercritical annealing cycle. So we're heating up at 5 degrees C per second up to, in this case, 775 degrees C, and I've drawn three diagrams of what could be going on at 0 seconds, 90 seconds, and 180 seconds of hold time. So we know at 0 seconds we're still ferritic. We have these big cement-type particles, which I haven't drawn in here because they're not really essential for this discussion. And we have a mixture of titanium, vanadium, carbonitride particles, which are these orange ones, the squares that I've put in here schematically, which are quite big, and they came from the hot band. And we have a distribution of very small vanadium carbonitride precipitates. Now, we know after 90 seconds of holding, we've started to form quite a lot of austenite. In fact, we're actually at the equilibrium fraction of austenite formation, almost, just a bit less than that. So I've drawn this here by, indicated this here by this orange line. This is supposed to be a grain boundary between ferrite and the new austenite that we formed during this annealing. Inside the austenite, what's happened is that these vanadium carbonitride precipitates are actually starting to dissolve, especially the smallest ones. The smallest ones dissolve first via the Gibbs-Thompson effect. Inside the ferrite, in contrast, it's completely different. The precipitates are not dissolving, they're actually growing, and there'll be some of them will be coarsening as well. So we can see that these small ones disappear in the austenite, and the smaller ones will tend to grow in the ferrite. So this final distribution at the end is what we would expect. We have very few fairly large precipitates in the austenite and a high density of precipitates in the ferrite. And it turns out, interestingly enough, that the mean radius in this phase and in this phase is actually the same. We can't really explain that at the moment. It's a very complicated phenomenon that we'll have to couple phase transformation modeling with precipitation kinetic modeling. And that work is actually ongoing at the moment. But the important point is that we have selectively strengthened this ferrite phase. So to come back to our original question, why do we see these differences in mechanical properties at the lower annealing temperature compared to the higher annealing temperature? Well, it's actually fairly simple. There are two things that happen as we go from this temperature up to this temperature here. First one, the volume fraction of intercritical austenite will increase. So the total amount of vanadium carbonitride precipitated will naturally decrease because of this dissolution effect in the austenite phase, which is more prevalent at the higher temperatures. Then the vanadium carbide, which does precipitate in the ferrite, is going to coarsen faster because you're at a higher temperature. And so it's less effective for ferrite hardening. So that explains briefly why this, we get this behavior with annealing temperature. Now the question would be, what could we do about that? There are various possible solutions, which I'll discuss later on. Thank you. The same technique can be applied to a different type of steels. These are called dual-phase steels, where we don't have any residual austenite. What we actually have is just ferrite and martensite. And this is an example of that, taken from using the trip steel chemistry. But what we did was we quenched it directly from the intercritical annealing temperature, and so we were in the ferrite austenite region. That gives you a two-phase final microstructure, which would be martensite and ferrite, a dual-phase microstructure. And again, you can see on this right-hand diagram, the ferrite in that case is very strongly strengthened by a high density of vanadium carbonitride precipitates, whereas the austenite, which has now become martensite after the quenching, has very few precipitates in it. So this type of strengthening behavior, the selective strengthening of ferrite, also works in dual-phase steels. And there's no reason at all why it shouldn't work with other steels, maybe third-generation steels, for example, if they are intercritically annealed and subject to fast cooling and quenching treatments. Okay, so that's all for this section. And I'll talk about dual-phase steels, in particular very high-strength dual-phase steels, above 1 gigapascal. First thing I want to say about dual-phase steels is that they're currently the most successful high-strength steels used in automotive applications. This is data which was provided by the Steel Market Research Institute, and it's from 2000 up to 2009. And what you can see is it's a breakdown of the market share of different types of advanced high-strength steels. So we have trip steels, complex phase steels, martensitic steels, boron steels, and dual-phase steels. The dual-phase steels are in blue. And what you can see is that the dominant market share has been, since 2000, has always been dual-phase steels, and it's more than 2/3 of the current total market for these high-strength steels. We can see a prediction on this this slide here, which is from, again, for the year 2020. And in that case, what you can see is that the predicted market share of dual-phase steels will remain about the same. Although we've got all these other new steels, second generation, third generation steels coming in and fighting for places in the automotive body in white, if you like, the chassis parts as well. The main material will remain dual-phase. So it's a very, very important material to study, and if we can introduce vanadium into that particular type of steel, it would be extremely interesting from a production point of view. Here's an example of the microstructure of a dual-phase steel. This is a TEM image. So it's a thin foil this time, it's not an extraction replica. And you can see the two phases here. The phase with the wavy lines in it, this light phase here, this is ferrite. And these wavy lines are actually bend contours. It's an artifact that you can see inside the TEM. And this darker phase here, where you can see there's a lot of contrast in there, that contrast is actually due to dislocations. This is a hard martensitic phase. This is the reinforcing phase. And the thing to note is that these martensite islands are very small. They're only a few, maybe a micron, sometimes much less than a micron in size. So this particular steel, the chemistry is given below. It was 0.15 carbon, 0.2 silicon, 1.9 manganese, and 0.2 chrome steel. And this was annealed at 760 degrees C, so it's about the same annealing temperature as we used for the trip steel in the previous example. Held for 130 seconds and then water quenched. And this one had 38% of ferrite in the final microstructure. And the reference for that you can find below. On this slide, I'd like to show you some of the mechanical properties of this steel from the previous slide. So here are two graphs. On this graph here, on the left-hand side, we're plotting ultimate tensile strength as a function of tempering temperature. And so here there are 4 different intercritical annealing temperatures that were studied. The 760 degrees C, which is on the red curve here. The green curve is 790. The blue curve is 810, and the grey curve is 840. Now the 760 was the steel that I showed you in the previous slide, and it had 38% of ferrite phase in it. As we increase the intercritical annealing temperature, the amount of ferrite will decrease until at this 840 degrees C point, we have virtually no ferrite left. It's like 99% martensite. Now, these steels were actually tempered, and what we would do is we temper them for 240 seconds at different tempering temperatures between, we would say, about 220 up to 470 degrees Celsius. And you can see that when you do that, the ultimate tensile strength decreases quite strongly in all cases. So this is mostly due to tempering of the martensite. If you look at the yield strength under the same conditions, the behavior is quite different. What you actually see is that the yield strength will increase with tempering temperature up to a certain maximum, and then it starts to decrease again. So for steels where there's a lot of ferrite, that's due to static strain aging in the ferrite. But for steels up here where there is no ferrite, this is a strengthening effect of martensite with tempering. And that's actually not very well understood. It could be due to some kind of incomplete segregation of carbon to dislocations during the quench, and this is completed by the tempering step, so you get a residual, an extra hardening effect. But we really don't know, to be honest with you. There are a few explanations that are possible. All I want you to understand is that it's actually quite complex, the behavior that you get. Dual-phase steels are very good in terms of strength and ductility, but they have one drawback, especially when you get to high-strength dual-phase steels, is that their damage resistance is actually quite low. What's happening is that because you have these two very dissimilar phases, you have the ferrite and you have the martensite phase, when you strain the material, there is a strain partitioning effect. The martensite will not deform very much, and the ferrite wants to deform a lot more. So at the interface between the two, you can nucleate voids very quickly, and those voids can grow to become cracks, and essentially the material will fail at a very early stage of deformation. That is a real problem with these steels, and the way we characterize it is we use this hole expansion coefficient. What we do is we take a thin sheet of the material in the quenched or the quenched and tempered condition. We punch a hole in it, usually about 10 millimeters in diameter, and then inside that hole we insert a conical punch with usually a 60-degree angle, and we press the punch into the material, which is going to expand the hole. The diameter will increase, and we stop the test when we see a crack that traverses the entire thickness of the material when viewed from above. Then from that we can calculate the ratio, the difference between the two diameters, divided by the original hole diameter, and we get this hole expansion coefficient. So the better, the more ductile the material, the more damage resistant the material, I should say, the higher will be the value of the hole expansion coefficient. So here we have the original steels in the as quenched condition at the 4 intercritical annealing temperatures that we've chosen. So I remind you, here we have 38% ferrite. Here we're going up to almost less than 1% ferrite, so it's almost purely martensitic steel. And what is interesting, and what you would not expect really from intuitively, is that the steel with no ferrite, so no soft phase, a very, very hard steel which has very low ductility, has actually got the better hole expansion coefficient. And that's because you don't have this dual phase structure, you don't have these interfaces where you have this strain partitioning. So a single phase martensite is actually better than a softer dual phase martensite ferrite steel in this particular damage resistance or this damage measurement experiment that we do. Then as you temper the steel, you can see that all of these are improved, and quite significantly. So you can have a very low, very brittle, if you like, steel where you had only 10% of hole expansion capability, and it goes up to 60, 70%, which is very, very good. This is the reason why high strength dual phase steels are very often tempered. From that you can make what we would call a process map, so a process properties map. So in this case, again, I've taken hole expansion coefficient and I've plotted it against ultimate tensile strength, and we've used the 4 different annealing temperatures. So there's only one composition. I must remind you, this is all done with one composition of steel. So we have the different colors representing the different annealing, intercritical annealing temperatures, and we look at how they vary as a function of tempering temperature and time. And this is that gives you this process map that we can show here. So let's take an example. We want to make a dual phase 1180 steel. Then that would be positioned here along this red line. Depending on how we process that steel, from the same composition, we can have a hole expansion coefficient of about 20%, or we can go up to 80 or 90% just by varying the intercritical annealing temperature and the tempering temperature. So it's to show you that the final properties are very, very, very sensitive to these microstructural characterizations. Now the question that I wanted to ask, I'll go back to this slide again, is this is for a single composition of steel. So what would happen if we change that composition and we added vanadium to the steel? So that's what I'll show you on this slide here. Now, this is very interesting. If you look, let's just concentrate on the red dots, the red points for the moment. So this is the steel with 38% ferrite. We've annealed it at 760 degrees C, and we have a very low hole expansion coefficient. It's only about 10%. And if we temper it here, then what will happen is we'll follow this dotted curve here. So we'll improve the hole expansion coefficient significantly, but we'll soften the steel as well because we're essentially tempering the martensite. If we added vanadium, then vanadium has a very well-known effect. It reduces temper sensitivity of martensite. That can be seen on the graph on the right. I won't go into this in detail. Please, I can give you a reference later on. But it will be, it's well known. It's a well-known property of vanadium that it actually reduces the softening of martensite during tempering. So that, in that case, what would happen is that this dotted line, if we added vanadium, it would actually shift, and it possibly would follow something like this, the line I've indicated here. And then for all these other intercritical annealing temperatures, where there's even more martensite present, that behavior would be the same. So we've shifted this process map from this point here. This corner would actually go up into the area that's more interesting to us, where we would have higher hole expansion and we would have higher strength. There is an assumption here which needs to be that's proved experimentally, it hasn't been, is that if we reduce the temper sensitivity of the martensite, for example, by using the vanadium, we still keep the same gain in hole expansion that we obtained due to tempering. And that needs to be proved. So we don't actually know that for sure. Experiments need to be done. That's not the only benefit that we would have from the vanadium. There is this other property, which I spent some time describing in the trip steel, where we have selective strengthening of the ferrite. If you remember, this microstructure here is actually a dual phase microstructure, and we strengthened the ferrite and we didn't change the martensite at all. So now, let's assume that we can do the same thing in this dual phase steel. What would happen? First thing is that we would have an overall increase in the ultimate tensile strength at the same composition, same carbon level, I should say, because we strengthened the softest phase. So we would have a shift along this axis here. And then, one of the things that's known about dual phase steels is that the damage properties actually improve as you reduce the difference in hardness or in strength between the two constituent phases, between the martensite and the ferrite. That's shown on this experimental graph here on the right. So what plotting along this axis here is the difference in hardness between the martensite and the ferrite phase, and up here is the measured hole expansion coefficient, and you can see you get a strong improvement as you reduce the difference. And that's quite logical. We're reducing the strain partitioning, we're reducing the damage formation. So if we could do that, then that would naturally shift this graph up the way, up this axis here. So the combined effect of those two different mechanical behaviors would be to shift this graph some angle, which could be 45 degrees, we don't know, up towards this top right-hand corner of the graph, which is exactly where we want to be, high hole expansion and high ultimate tensile strength. So what I'm saying is that the probable effect of vanadium additions by selective strengthening of ferrite will reduce the hardness difference between martensite, and it will improve the damage resistance. So it would be a very, very interesting thing to do to a high-strength dual-phase steel. Let me just make an intermediate conclusion on that. Dual-phase steel properties depend very strongly on the microstructure, and that's controlled by the intercritical annealing and by the tempering temperatures that you employ. Vanadium additions could greatly improve the balance that we obtain between the ultimate tensile strength, the ductility, and the hole expansion ratio. for the reasons that I showed you in the two previous slides. That would be excellent from two possible points of view. First thing is we could make higher strength, higher ductility steels, or what we could do is keep the same strength and ductility ratios and damage ratios, but use a lower carbon content, which would make the steel more weldable, for example. The reason for those improvements would be improved tempering behavior in martensite and also to selective strengthening of the ferrite phase. So I believe very strongly that the effect of these vanadium additions on processing maps is something that we should be studied, and we hope to be doing that next year in a project at the CanmetMATERIALS laboratory. And I'll come to the last application, which is a different type of microstructure. This is high manganese twip steels. Now this is a product that I worked on for a long time when I was at ArcelorMittal, and we studied three different alloys. Iron with 17% manganese and 0.9 carbon, iron with 22% manganese and 0.6 carbon, and iron with 18 manganese, 0.6 carbon, and 1% aluminium. This graph here shows the ultimate tensile strength against strain curves for these steels, and what you can see is they have an enormous amount of strain hardening. They're very ductile. There's a wide range of possibilities, and the one which shows the highest strain hardening was the 17% manganese, 0.9 carbon steel. What I would point out to you is that although these steels are fully austenitic and they have a very high ultimate tensile strength, they do have a very low yield strength. And if you're looking at applications for automotive, for chassis, body in white, safety related applications, crash applications, then you really do need to have a higher yield strength. Probably the minimum would be 700-800 megapascals that you want for most of these applications. So we need to find some way of strengthening these steels if we want to use them directly in the body in white. Now that could be done in different ways. We can do it by strain hardening, because we actually deform the parts, or we could do it by reducing the grain size, but we hit a technological limit on that, which was due to cold rolling, and you can't really decrease rolling forces. You can't really decrease the grain size below about 3 microns in those steels. It's a technological limit. So it would be very interesting to increase that strength using a different technique, which would be precipitation strengthening. So the question would be, what precipitate would you like to use? And I want to show you that the one that's best to use is vanadium. Here is a kinetic precipitation diagram. This is calculated using the multi-Preci model, which was developed by Philippe Mogis and Mohamed Gouni at ArcelorMittal. And what it shows you is the PTT curves, precipitation time temperature curves, for this alloy here, iron 22 manganese, 0.2 silicon, 0.6 carbon, with 100 ppm of nitrogen and 0.2 weight% of vanadium. Now, superimposed on the diagram, there are two dotted lines. I hope you can see them. The one on the left-hand side would be the typical cooling curve for a hot strip after hot rolling, where it would be coiled around about between 400 and 500 degrees C. And the other one would be the temperature and the time that we would consider using in an annealing step after cold rolling. So it would be recrystallization annealing, which would be round about 800 degrees C, maybe between 800 and 850 degrees C, for less than 200 seconds. First thing I want to point out is that in the hot strip, this curve here, the blue curve here is the time and temperature at which 1% of all the vanadium has been precipitated. Going up to the red curve here, where we have almost complete precipitation, 90%. This thermal path followed by the hot band after hot rolling and going into coiling, it doesn't actually, just barely touches the 1% vanadium curve. So you would expect to see no vanadium precipitated in the hot band, in the hot coiled band, which is exactly what you want, because we don't want to strengthen that band. We don't want to have an increase in cold rolling forces. And then the cursors disappear again, as usual. And then in the cold, after cold rolling, and we do this recrystallization annealing, you can see that what we would be doing is we'd be intercepting this orange curve, and that would be about 50% of the precipitated vanadium, which is very interesting. So it means that we can not change the strength of the material right up to the end of cold rolling, and then we will strengthen it during recrystallization annealing, which is exactly what we want to do. This is the hot strip. These are the hot strip properties, measured hot strip properties on one of these steels. And what we're looking at is the variation as a function of the amount of vanadium that we added. So you can see that the ultimate tensile strength, which is the dark green or dark blue curve here, and we have the total elongation here, which is red on this axis, and then we have the yield strength here. Very little change in the amount of vanadium as a function of the amount of vanadium that's added up to 0.4, which is very high, 0.48%. So it shows that most of the vanadium, almost all of the vanadium in this case, is maintained in solid solution. We don't get any strengthening effect from it, which is exactly what we want. You couldn't do this with a different precipitate like niobium or like titanium because they're much less soluble in the austenite. After the cold rolling and annealing step, what we found was that we got some very interesting properties and very interesting precipitation microstructure that formed. This is a TEM extraction replica here, showing a very high distribution, very fine distribution of homogeneous vanadium carbonitride precipitates, and they're very small. And you see occasionally larger precipitates, but they're actually in the minority. This is the size histogram measured at various points on two industrial coils. So these are actually industrial data. So you see the two different colors represent two coils. Very similar behavior. What we see is that the mean precipitate radius is very small. It's only 3.7 nanometers. So we would expect a very good strengthening effect from those precipitates in this type of steel. We actually confirmed that because the problem with TEM data is there's always an argument, is it representative at such a very small volume that you're actually analyzing? So we took a bigger sample, thick samples, and did neutron scattering. This was with the aid of Benoit Marat, who was at the University of Grenoble. And what we found using the neutron scattering data was that the mean radius was 3.8 nanometers compared with 3.7 nanometers measured in the TEM, so we were very happy with that result. If we look in more detail, again, this is another extraction replica. What we did was interrupted heating after cold rolling, heating and quenching experiments. So we're looking at how the vanadium precipitates between the end of cold rolling and the start of the isothermal holding during the recrystallization annealing, and how does it affect the recrystallization kinetics. First thing I would point out to you in this particular extraction replica image is that some of the precipitates, the very fine ones, seem to be aligned. You can see them here. I've marked them out with two little arrows. These are precipitates that are formed on a dislocation, and that dislocation was something that had to come from the cold rolling, and so that suggests very strongly that these precipitates formed before recrystallization, so during the heating stage after cold rolling. Here what we can see is the recrystallization kinetics curve. So we measured the recrystallized fraction as a function of temperature. And below that, what we have is another curve where we did selective chemical dissolution, and we're looking at the amount of vanadium precipitated as a function of temperature as we were increasing, going up this recrystallization annealing step. And what we found is that if you look at the amount of vanadium that's precipitated, this is in weight ppm here, it's actually quite low until we hit this temperature here, which is, I think it's 720, something like that, 725. And there's a sudden increase there. So that means this is when the vanadium carbonitride precipitates really start to nucleate. And this goes up here. And if we went into this curve, would keep going as we go into the isothermal part of the recrystallization annealing step. At that same temperature, that's 725, you can see there's a kink, or there's a slowing down of the recrystallization kinetics. So it means that there's an interaction between these precipitates and the recrystallization behavior of the material. Again, it's further proof that these things are forming on the way up and are not really forming during the isothermal annealing step. So that would be very interesting, because we would expect a much higher precipitation density when they're formed heterogeneously on dislocations in this case. I've shown you that the hot strip properties didn't change as a function of the amount of vanadium added. Well, the cold strip properties certainly do. And this is an example, again, industrial steel, where we had a reference steel with 22 manganese, 0.6 carbon, which would be the pink colored curve, and there was the same steel but with microalloyed with 0.2 vanadium and with 100 ppm of nitrogen. And you can see that we got a strong increase in yield strength, 150 megapascals, and we have a 100 megapascal increase in the ultimate tensile strength. The flow curves are more or less parallel, so there's no major change in the strain hardening mechanism. We don't see a big decrease in ductility. So it's a very interesting effect that the vanadium has had there. And here is this similar data, but this time as a function of the amount of vanadium that we add. So you can see that the ultimate tensile strength as we go from 0 vanadium up to, well, in this case we added 1%. The ultimate tensile strength was improved by over 350 megapascals at 1% vanadium. And also the yield strength could be increased by 450 megapascals. So it's a very, very strong strengthening effect. In all cases, the total elongation was above 35% here. Now you might say, well, we could possibly do that with something else. We could do it with vanadium, or we could do it with niobium, or we could do it with titanium, and they would be, would add less, it'd be cheaper, etc. So here is, we actually tried that, and here is the results of those experiments. It doesn't actually work. Now, if we look at the curve with the black diamonds, is the measured mechanical properties as a function of the amount of titanium additions that we put in. And you can see that it works very well for the additions up to about 0.1 weight%, and then it saturates. We don't get any further increase in strength for more titanium. And that's because essentially all of the titanium is coming out during the solidification. There's a big blocky TIN, and it doesn't add to any strength. So you really can't exploit the potential of titanium in these steels. The grey square at the bottom is niobium, this one here, where we tried to add 0.3, a bit over 0.3 weight% niobium. And what we found was that we did get quite a lot of precipitation, but the precipitates tended to be very big. They tended to be about 30 nanometers in diameter. And so they're not very effective as strengtheners. And we tried various heat treatments, various types of recrystallization, annealing, cooling. We couldn't really do anything about that. So it seems to be ineffective for strengthening. And the triangular points, those are vanadium data from two different types of steels. So one where we had 22 manganese, and the other one where we had 18 manganese. You can see they more or less superimpose each other. And the strengthening is very effective, and it doesn't saturate, unlike the titanium. So we would say that vanadium is the best strengthening precipitate for these types of high manganese steels, and it could also be applied to medium manganese steels and newer steels, about 10% manganese. This slide here, we're just looking at the flow curves of different types of different compositions with the different microalloying additions. So I won't go into this in great detail because there's a lot to say about this, and we really don't have all that much time. But what I would say is that the flow curves tend to superimpose. So as you're adding titanium, vanadium, or niobium, you don't really seem to be changing much the strain hardening mechanisms until you get to some very high compositions. So I've tried to indicate those with the little black arrows, where the actual flow curves tend to diverge and they tend to saturate. So that would suggest that at these higher strains, we're actually changing the hardening mechanism. And the hardening mechanism of these steels is essentially twinning, twin formation. That's why they're called twinning-induced plasticity steels. So there is some interaction between precipitation and twinning, but it seems to occur mostly at higher strains and mostly when you add higher amounts of microalloying element. Now this is, we tried to investigate that, so we went to the synchrotron. This was work done by Jean-Louis Collet during his PhD. And what we were looking at here, this parameter alpha plus beta that we're plotting is essentially related to the number density of stacking fault or twinning planes in a certain direction, in the 110 direction in the austenite. And we're plotting that against true strain for two different alloys. One would be the reference alloy with no vanadium in it, and one would be the alloy with 0.2 vanadium. and that's the red curve, and the blue curve is the reference one. So you can see that up to about 20% of strain, there is no difference no real difference in the twinning kinetics, if you like, between the two steels. But after 20% strain, there is a saturation in the precipitation data, which explains the change in the flow curves. What is actually happening is that there is an interaction between stacking faults and between very small precipitates, and there is some very nice recent work being done by Yen and Huang. I give the reference on this slide here, where they are looking in detail using very high resolution TEM experiments at how stacking faults interact with precipitates. And if you know how a stacking fault interacts with the precipitates, then that gives you a clue about the twins, because the twins are essentially, the nucleus of the twin is obviously a stacking fault. So again, I won't go into it in great detail because of time limitations, but I would encourage you to read the paper. They used that data to do some structure properties modeling. And so these two graphs here are some of their first results, micromechanical modeling, showing the interaction of precipitation and twinning for a reference steel with no vanadium and the same steel with a high amount of vanadium added, 0.87 in this case. So what you can see is that when you add the vanadium, they do see quite a strong change, or a reasonably strong change in the strain hardening behavior. Again, but they do have parallel tensile behavior here. So the model is I think it would be the points, and the experimental data is given in the line, the blue line and the red dotted line. And you can see the agreement is actually very good. So we think that we're actually improving our understanding of that phenomenon. So what I'd say is that vanadium additions have very interesting properties, and they could be applicable to a very wide range of advanced high-strength steel grades. Some of the things that you can do with vanadium include selective strengthening of ferrite if you have multi-phase steels with intercritical annealing steps involved in the production. You have improved hardenability, which is something I haven't been able to talk about. You have improved bainite and martite tempering resistance and improved martensite ductility. Those are other factors which I haven't all been able to touch on in this talk due to time constraints. But they're all potentially accessible using vanadium technology. Certain aspects of it can be extended to the new steels, generation 3 steels. I would take, for example, the 10% manganese trip grades, which are recently being shown by Lee and Dukuman. Some of those have got vanadium precipitation strengthening in them. I think there's a strong case for studying much in more detail vanadium additions in high-strength steels. If there is one last area where we haven't even looked at it, but there is a strong interaction between vanadium precipitates and hydrogen embrittlement can be a big problem in these steels. So that is a completely different subject which would merit a talk on its own. Anyway, I hope I've given you an overview of some of the possible applications, and that it would encourage you to give it a try. Thanks very much for listening.